First of all, you should probably know what organic chemistry is. Well, turns out that just about everything that is living in this world is made up of these carbon compounds, right? We've got carbon with a little bit of nitrogen, oxygen, and a whole bunch of hydrogen thrown in. So let's first of all define organic chemistry. So here we have the definition. Hopefully you can actually read all that. It's the chemistry of carbon-containing compounds plus some nitrogen, oxygen, and a whole bunch of hydrogen, some other stuff thrown in. That's really all there is to it. The interesting thing about organic, though, is all the chemical principles that you learned also apply here. Because really, if you look at the chemistry of life, this is going to apply to, 99% of what you guys are going to study. A lot of the people in an organic class obviously are going into some sort of health field, either that or they're masochists. But one of the things we'll notice, these carbon-containing compounds can form these big, long chains, and that's actually a rare thing for an element. Sulfur does it a little bit, a couple of other elements do it, but it's not to the extent that carbon does. So that's what leads to organic chemistry. Some pretty important core concepts from your general chemistry days are these two terms, valence electrons and the octet rule. So hopefully this is not the first time that you've heard those, but it may be a little bit hazy in your brain about what the heck that is. So valence electrons are the most accessible electrons in an atom. So let's look at carbon, right? So here's a carbon, and if you remember, there's this Lewis dot electron structure. One of the things that we did to represent carbon's number of valence electrons is we put these little dots around carbon, right? And so these valence electrons are what's called the outermost electrons in that carbon. Of course, there's other electrons, in the case of carbon, 2 other electrons that we don't really care about in the inner core, right? I kind of think about chemistry as kind of being inherently lazy, right? We do the easiest stuff to do is kind of on the outside, so that's where most of the action happens. And one of the things that you'll notice is that if we look at this Lewis structure of carbon, there's not enough electrons there, right? And so we'll kind of briefly review a couple of different modes of bonding. The one that's going to be the most important to us as organic chemists is in fact covalent bonding, where instead of this carbon losing or gaining any electrons, like what would be true in an ionic compound, usually these carbon compounds will share electrons with other atoms. Right? And so the reason that carbon has to share those 4 electrons is this thing called the octet rule, right? Everything that, well, I shouldn't say everything, but the majority of processes we see all have to do with different atoms trying to get to that perfect 8 valence electrons, right? And that's called the octet rule. It's the reason that anything happens, really, is to make sure that we put some sort of bonding environment around carbon or any other atom that allows us to satisfy the octet rule. Anybody that wants a little bit more of this, just let me know. I've got a link to a whole bunch of different videos on the Mulleted Chemist YouTube channel that'll kind of help you guys out with that. Okay, so we have our carbon with its 4 valence electrons, and as I said, carbon, pretty much all of organic chemistry in terms of carbon are going to be covalent bonds, right? And so I'll just kind of try to remind you about a couple of things, and we'll start with a really, really simple carbon compound that we're going to call methane. It's the primary component of natural gas and things like that. And so what we can do is, if we're this parent carbon, right, and we've got our 4 valence electrons, what I can do is I can recognize that there are other things in this universe that are also fairly unhappy, and they don't have the octet rule being satisfied. In this example, I just, instead of representing the valence electrons of a hydrogen as a dot, I just put an X instead, so we can kind of keep track of them. One of the things you'll notice very quickly is that, it doesn't really matter that we keep track of these electrons as belonging to hydrogen when we get into some future stuff. But that's on the way. Right now, it just may kind of help you to see how everything comes together into a covalent bond in case you don't remember. So what this carbon does is it recognizes, hey man, I don't have my octet, but I have all these hydrogens that have their 1 valence electron. So let's set up a situation where we can share these things, and I as a carbon can actually get to 8, right? And so what we could do instead everything could come together to look like this, which is actually methane. But this is probably not the way that we're going to represent methane very often. It's kind of a pain to keep track of all those little dots. What we're going to do instead is we're going to represent this thing with single bonds, like this. And one thing that's really important, an important core concept, is anytime you draw a line, that is specifically telling you that there are 2 electrons being shared right there. Right? And so this carbon right now has satisfied its octet. One thing that's interesting about hydrogen is always the exception to things, is the weird thing is that hydrogen has actually filled its outermost shell by just getting 1 additional electron from carbon, right? And so hydrogen is one of those weirdos that only needs 2 to satisfy the octet rule. The octet rule is actually not a very good, I guess, way of talking about it. We should call it the full valence electron rule or something like that. But the point is that hydrogen's happy with its 1 bond, and carbon is happy with 4 bonds. And that's one of the most important things from today's set of lectures, that you guys recognize that carbon, at least without any kind of charge, has 4 bonds. It loves to bond 4 times. And that's going to really help us when we have to start drawing carbon compounds, which you'll start to see in just a second. But what happens if my carbon, which likes to bond 4 times to satisfy its octet, what if instead of bonding to another carbon in this thing called methane, what if instead it bonds to another carbon, right? So let's take a look at what that looks like. So now we've got both of these carbons being happy, right? They still have satisfied the octet rule. And what you'll notice is that both of those carbons right there that have a satisfied octet rule are actually now bonded together. This kind of chain formation is called catenation. It's really what gives rise to the chemistry of life, right? The fact that we're just bags of these, of water and a whole bunch of different carbon backbones with various things sticking off of them, right? Like that's what an enzyme is just a whole bunch of carbons and some other elements all just kind of all congealed together in a big giant booger, but it just happens to be a fairly useful booger. So this guy is called ethane. And hopefully you guys can see that. Probably notice that the beginning usually tells you the parent chain, in other words, how many carbons are in there. Anything with 2 carbons gets an eth. The ending in organic chemistry usually tells you what I call is like, is there any sexiness in there? A&E means there's no sexiness. Other endings indicate there's some sort of functional group, in other words, some sort of atoms that we can do something exciting with. But alkanes are pretty boring. You pretty much just burn them. Before we go on, what we have to talk about is this is a very boring kind of flat structure, right? This doesn't show us any kind of angles or what this thing actually looks like in 3-dimensional space. So that's where a knowledge of valence shell electron pair repulsion theory, or VSEPR theory, or kind of more easily known as like molecular geometry theory, comes into play. And the cool thing is we have these special little Lego kits called molecular model kits that I'll show you on the very next slide. And I'll show you some of the kind of interesting things about this, these 2 carbons. Okay, so I've built you an ethane with my little model kit here. And so I'll get close to the camera. Oh, necessary zoom! Right? And what you'll notice is that there's all kinds of different angles there that are not really correctly represented by that drawing up there. But what we're going to start to do is start to use wedges and dashes, which are another important part of organic chemistry. It turns out that organic chemistry is 3-dimensional. I'll step away from the camera so you can't see up my nose again. And another cool thing about these little model kits is you can notice that if I can rotate my model kit, that tells me that this thing in real life can actually rotate about that bond, right? And so how are we going to represent this thing? Well, there's a couple of different ways that we could do it. But what I'm going to do is kind of hold this thing in a certain conformation, right? In other words, a certain relationship here where everything's kind of eclipsed there. And we're going to start to put in a little bit more detail. We're going to actually indicate those bonds, their 3-dimensionality, and we're also going to indicate we go. We're also going to indicate their kind of relative arrangement, right? There's angles here. It's good to know, since we already decided that carbon was bonded 4 times, that that carbon that is bonded 4 times, in this particular case, since I've got bonds to 4 individual atoms, that's what gives rise to something called the tetrahedral geometry. And so let's write that down. We'll write that in red. So if somebody said, indicate the geometry, somebody, that's me, I guess, said, indicate the geometry about a carbon. In this particular case, the way that I did that is I said, okay, are there, atoms, 4 different atoms bonded? And if they are, I know that that's based on what's called a tetrahedral electron domain geometry. And if all of them, right, are atoms, that's what's called a tetrahedral geometry. Another important thing about tetrahedral geometry is you'll kind of notice, if you look at that tetrahedral geometry, let's highlight this angle right here, right? You'll notice that it's a little more than 90 degrees, right? It's not the 90 degrees that we represented up here. It's actually 109.5, or very, very close to it. So those are kind of 2 things that at the beginning we're really going to work hard to kind of use. Is we're going to try to assign molecular geometries, because that tells us what something looks like in 3-dimensional space. We're also going to kind of relearn those bond angles. The only really hard one is tetrahedral, is just right around 109.5, and of course there are different factors you probably remember from Gen Chem where that might condense a little bit or it might expand a little bit. But we don't really care. So what we have are 2 different tetrahedral geometries bonded here. But what I'm going to show you in the next example is that carbon, not only can it form chains that are, any number of carbons long, but it can also adopt a couple of different geometries that we'll talk about. All right, here are a couple other simple organics that we can talk about, a couple of different geometries with. Right, there's carbon and its tetrahedral geometry. This guy, this functional group, by the way, we might as well just start using functional group names. We'll write it in blue here. This guy right here is called an aldehyde. And again, there'll be a separate video where we kind of talk about all the different functional groups that we should really start to memorize with note cards. But for now, it's just an introduction. So an aldehyde is any time you've got this guy, which is called a carbonyl carbon, in other words, a carbon bonded to an oxygen, a hydrogen on one side, and some sort of simple carbon on the other side. Right? And so that would be called an aldehyde functional group. But the interesting thing about, well, to me anyway, the interesting thing about an aldehyde functional group is that it is no longer a tetrahedral carbon. It's still a carbon bonded 4 times, right? But now there's only 3 different atoms that are bonding to it, and that is where we get what's called the trigonal planar geometry. And the trigonal planar geometry is called a plane because it just kind of lies flat. And instead of having 109.5 degree bond angles, now there's a 120 degree bond angle right there. And there's a 120 degree bond angle. There's a 120 degree bond angle. But that geometry is very different than this tetrahedral carbon out here that has those 109.5 degree bond angles. So what we're kind of building, like if you imagine this like really simple example, if you expanded it to a huge amount with all kinds of different geometries, that's where you end up with things like enzymes, right? Where the enzymes are kind of held in a certain orientation where different substrates can kind of fit into them properly. This is where all that kind of 3-dimensionality comes into play, is because of the geometries of these carbons. This guy, right, this by the way is called a nitrile. That type of functional group. And that carbon, you'll notice, is only bonded to 2 different atoms. Still bonded 4 times, but only to 2 different atoms. And that's what gives rise to what's called a linear geometry. So before I kind of stop talking and go to the kind of the more whiteboard, like the electronic whiteboard that I'm going to write on and show you a different way of presenting information, I wanted to actually show you 3-dimensional model kits of these guys and compare it to ethane, assuming I can find all the pieces that my kids keep trying to lose on me. So hold on one sec. Okay, so there's the aldehyde. And hopefully you can see right there. And you'll notice that those 3 things bonded to that carbon right here are actually in a plane, right? They kind of just lie flat. Whereas this tetrahedral one right? That actually has that three-dimensionality. And then we can also take a look at the nitrile over here that I said is linear, by the way, 180-degree bond angle. That's what a line is. Right? And that's what that nitrile looks like. So the cool thing is, and actually one of the things that originally attracted me to organic chemistry, is the fact that I could use all these different Lego kits. Like, it's okay to play with Legos. In fact, in one of my favorite grad school proctoring experiences, well, it's funny that I have a favorite proctoring experience. I had one particular student, right? At Cornell, you have these huge lecture halls filled with, like, 600 students or something like that. I think the day of the test, there were maybe 200 people there in my building. And this girl brought this huge model kit in. And of course, everything is sloping. And what happens when you get stressed out, right? You start getting spastic. I'm spastic anyway, even when I'm not taking a test. And all of those little spheres all came down and gathered all around the front of the room where I was. And I just thought that was just awesome. She was livid. Bad day for her, but hey, I helped her pick them up, and it was worth the story. Okay, so I'm going to switch over to the electronic whiteboard there. Let me know if you like that better than this, or you like seeing my lovely face more. If one of the things I really struggle with is like the lighting here, there's always some sort of shadow. It's a really small room. So if you have any advice, just let me know, and I will see you in the next section of video.